Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome to the Deep Dive, where we take those technical concepts that you see floating around, the ones on the box when you buy a new computer, and we try to bring them into sharp focus. Today, we are tackling one of the biggest points of confusion in computing specs. It's CPU cores versus threads. You know your system needs more of them, but, what are they actually doing? Our mission today is pretty simple. We want to take you from just, vaguely recognizing those terms to being genuinely well-informed on the fundamental units that are driving all modern performance.
And this isn't just about simple definitions. We're actually going to get a bit historical here. Yeah, we're exploring why these things even exist, because the original villain in this story, it wasn't sluggish software, it wasn't slow internet, it was physics.
Physics.
Specifically the physics of heat. So we're diving into some technical notes here on definitions, the difference between the illusion of multitasking and the reality of it, and some of the incredible tricks engineers came up with, like hyper-threading.
So the big question we're really answering is this. How can your tiny little laptop run 20 heavy applications, maybe a game, and stream video, all at the same time without literally melting down? Let's unpack this. And I think we have to start with the most critical distinction of all, what looks simultaneous versus what is simultaneous. So when we talk about a computer doing two things at once, there's this almost philosophical difference in how it's done. And it dictates everything about how fast your system feels. It's the difference between doing two things at the exact same time versus doing them so incredibly fast, they look like they're happening at the same time.
That distinction is everything. It's concurrency versus parallelism. And it all hinges on one simple question. Do you have one engine or do you have multiple engines?
Okay.
Concurrency is the ability of a system to manage two or more programs in what we call overlapping time phases.
So it's the illusion of speed.
Yeah.
I'm picturing like a single, really efficient chef in kitchen.
That's a great analogy.
Right. He's managing multiple orders just by switching tasks every few seconds. Chop this, stir that, plate this.
Exactly. Concurrency relies on a technique called time slicing. The CPU works on task A for, say, a millisecond. It saves its progress, switches to task B for a millisecond, saves that progress, and just keeps repeating.
Okay, got it.
The crucial point, though, is that at any single given moment, there is only one instruction actually executing. If you look at older systems, with a single core processor, this was all they could do. It's a generalized approximation of real parallel execution.
But true simultaneous action, the thing that defines basically all modern computers, that's parallelism.
That's parallelism. That is the reality. Here, tasks are broken down into subparts, and you have multiple dedicated engines, multiple cores processing these subtasks at precisely the same time.
So that makes the distinction crystal clear. Concurrency is one core just switching really, really fast. Parallelism is two or more cores actually executing separate things simultaneously.
Yep. One is a magic trick. The other is true multitasking.
Okay, so that brings up a huge question. If those single-core processors could already trick us into thinking they were multitasking with concurrency, why did the entire industry pivot? They spent billions to figure out how to cram multiple separate cores onto one chip. What was so broken about the simple single-core model?
It was a crisis of physics. We call it the power wall or the heat wall. For decades, the main way to make a computer faster was just to increase the clock time.
Right, the frequency. The gigahertz number.
The gigahertz, exactly. And the thinking was pretty linear.
So if 1 gigahertz is good, 4 gigahertz must be 4 times better. Simple.
You'd think so, right. But sadly, physics doesn't work that way. The power consumption and, more importantly, the heat that's generated, it increases exponentially as you crank up that clock time. We basically hit a wall around the early 2000s. To push the clock speed any further would have required so much power and, frankly, ridiculous cooling systems like, think, industrial chillers for your desktop, that the processors just became completely impractical.
So we were literally at the physical limit of what silicon could handle.
About melting, yes.
So the solution wasn't to build one giant engine and run it at 10,000 RPM. It was to build two smaller, more efficient engines and run them both at 5,000 RPM.
That is precisely the multi-core solution. You create two or more cores on the same piece of silicon on the same die, and you increase the total processing power without having to push the clock speed of any single core into that catastrophic heat zone.
You just keep the clock speeds at a more modest, efficient level.
And that concept of efficiency, that was the real breakthrough.
I see.
Yeah, our sources confirm this trade-off is absolutely crucial. A modern processor with two cores running at a modest speed can actually perform instructions with a similar speed to a hypothetical single core running at twice the clock speed.
But the dual core uses way less energy.
Exactly. It uses significantly less energy and produces manageable heat. It was a complete victory of parallel architecture over just raw frequency.
And digging into the notes, they mention something that sounds small, but I guess is a huge deal. They say placing multiple circuits close together gives you shorter connections. Why does the length of a wire inside a chip matter to me?
It sounds like such a tiny detail, but it's fundamental. I mean, inside the core, instructions are just electrons moving around.
Right.
If you shrink the circuit, the connections get shorter. Shorter connections mean less electrical resistance, and that translates directly into lower capacitance and less energy wasted as heat. And maybe even more important, less travel distance means the whole circuit can work faster without hitting internal delays. It lets designers pack in way more transistors per choice.
More capability in a smaller, cooler package.
That's the whole game.
Okay, so we solved the heat problem with physical cores, or hardware engines, which allows for true parallelism. But that brings us to the next layer of complexity. How does the software, the operating system, know what to do with all these new engines? That's where the thread comes in, right?
Yeah. This is where most people look at their computer specs, 8 cores, 16 threads, and their eyes just glaze over.
Right.
Because they're two different things operating on two completely different levels of abstraction.
So let's define them cleanly then. We've established the core is the physical engine. What is a thread?
A thread is a unit of execution. It's a virtual component. Think of it as the thing that manages the flow of tasks within a process. So if the core is the physical factory floor,
The thread is the assembly line path, the work instructions.
perfect. It's the specific set of instructions the operating system maps out.
Okay, but if threads are just virtual, if they're just software instructions, why can't I just have an infinite number of threads on a single core? What's the physical limit there?
That is an excellent question, and it really gets to the heart of why these two concepts are so linked. While the thread is virtual, it still requires physical resources to store its state, its registers, its instructions.
I see.
So the operating system uses threads to manage the flow of work, but the number of threads that can be efficiently active at any one time is limited by the CPU's actual physical hardware. And that brings us to the key functional difference. Cores increase the overall capacity, the total amount of work you can get done at once. Threads improve throughput by making sure those cores are never just sitting idle.
So cores bring the parallelism and threads bring the organization.
You've got it. Cores bring the muscle, threads bring the management. The sources note that cores use content switching, which is moving the physical work to an idle unit, while threads focus on utilizing those multiple processing units to run numerous processes efficiently.
It seems like threads really need that multi-core structure to even show their full benefit.
They absolutely do. Which leads us to the term for how this all works together.
Multithreading.
Multithreading. It's the technique that allows a CPU to execute many tasks, but from one single, larger process at the same time. These threads run individually, but, and this is critical, they share the same memory space and resources within that process.
It's like the ultimate resource manager.
Right.
So if you have one huge job, like rendering a video, you can break it into, say, 8 parallel subjobs, assign a thread to manage each one, and if one of those subjobs hits a snag like it's waiting for a file from your slow hard drive, the core doesn't just stop.
It doesn't stop. It immediately switches to another thread that's ready to go.
Brilliant.
And the most relatable example of this happens probably 100 times a day in your pocket, on your smartphone.
Okay.
Think about when you open a big app, one that needs to fetch data from the internet. What do you see on the screen?
The little spinning wheel. The loading icon, the progress bar, something to show me it's working.
That is multi-threading in action. To your phone's operating system, 2 threads are running. One thread is doing the slow, boring job of fetching data from the network.
Okay.
The second thread has one job: render the graphical user interface, the spinner itself.
Ah. Because if the phone was single-threaded, it would just freeze.
Mm.
The whole screen would lock up while it waited for the data.
It would be completely unresponsive. Precisely. Multithreading ensures the system feels responsive even when it's busy. But, there's a little nuance here for the well-informed listener.
Good one.
Because these threads share resources, the system has to be really careful. What happens if both the data fetching thread and the GUI thread try to write to the same spot in the phone's memory at the exact same time?
Yes. A crash.
Conflict, at least. Potentially. This is why multi-threaded programming is so complex. The system needs these mechanisms, they're called locking or synchronization, to make sure shared resources are updated in a logical order. It gives you incredible speed, but it needs serious management to stop the threads from, tripping over each other.
And that complexity, that management, must have gotten even more intense when technology started to blur the lines between what's a physical core and what's a virtual thread. I'm thinking of hyperthreading. That always felt like a historical cheat code for performance.
It absolutely was. It was a breakthrough born out of total necessity. Hyperthreading was Intel's answer to that power wall we talked about way back in the early 2000s with the Pentium 4.
Right, and back then they were stuck on a single CPU core.
Stuck. They desperately needed some form of parallelism, but they couldn't just add a second physical core without dealing with all the cooling challenges.
So how do they pull off this fake out?
They did it by fooling the operating system. Hyperthreading essentially takes a single physical CPU core and it adds a set of registers and some extra control circuitry. So to the operating system, it looks like there are 2 logical CPUs for every 1 physical core.
The OS is completely convinced it has twice the number of actual engines.
Completely. So if you have a 4-core CPU with hyperthreading enabled, your operating system sees 8 cores, and it starts assigning up to 8 threads to those, logical cores.
And there has to be a but, the actual hardware underneath, the execution resources, the math units.
Yeah.
That's still just one shared component, right?
That is the big caveat. It's not 2 physical cores. It's 1 physical core with 2 threads competing for its resources.
So if both threads running on that one core need to do, say, complex math at the same time,
they have to wait their turn. They're queuing up for the same resource. The real benefit of hyperthreading comes from leveraging downtime or latency.
Okay.
Whenever one thread stalls, maybe it's waiting for data to load from your main memory, which is super slow in computer terms, the CPU instantly switches its execution pipeline over to the second thread. It just keeps the physical core busy. It's an efficiency play.
That sounds like a brilliant way to mask that downtime. But since it's sharing, it can't be a true 2 times performance increase, can it?
Oh, not even close. Far from it. In the best case scenario, where you have lots of threads that are stalling for different reasons, hyperthreading might give you a 20, maybe 30% speed boost.
That's still pretty good.
It's great. But if the tasks are already hammering the CPU or they both need the same resources, the overhead of switching between them can actually sometimes slow things down.
Yeah. That's why you'll sometimes hear of, power users or hardcore gamers actually disabling hyperthreading for very specific tasks.
Yeah.
It's a fantastic efficiency booster, but it is definitely not a free second core.
This has been a really fascinating look under the hood. So to summarize the whole hierarchy here, parallel execution, doing 2 things at once, truly, that requires multiple cores. Those cores are the physical hardware engines. They're the solution to the heat crisis of the old single-core design.
And the work itself, that it's managed by threads, those are the virtual components, the coordinators that improve throughput and speed things up by making sure the hardware is being used as efficiently as possible.
Even using clever historical tricks like hyperthreading to hide any downtime.
Exactly.
He started this by talking about how the multi-core design solved that efficiency problem. It avoided the insane heat from just cranking up clock speeds, and that in turn let designers pack in more transistors per choice. The architecture of every computer you own is a result of managing heat. Which brings us right to the present. If the multi-core system solved the clock speed bottleneck, what is the next great physical wall we have to overcome? Just adding more and more physical cores is starting to see diminishing returns. It's just getting too complex to coordinate them all.
So if the answer isn't just more cores, what's the next bottleneck after the core count? Are we looking at totally new types of transistors? Or maybe a strange pivot back to maximizing single-thread performance through entirely new kinds of processing units? It's something to think about the next time you look at a spec sheet that boasts, say, 64 threads. Are you really running 64 separate jobs or just 32 very, very efficiently managed ones? Thanks for diving deep with us.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.